4.4.2 The Conjugate Root Theorem. Leaving Cert Mathematics, Higher Level Only. This video was produced by the UCD Math Support Center in conjunction with the UCD Access Center. So in this slide we're going to look at something called the Conjugate Root Theorem. And remember, theorem just means a rule. So this is saying if z equals a plus bi is a root of the polynomial f of z with real coefficients, then the conjugate of z, or z with a bar across it, equals a minus bi is also a root for a and b are real numbers. So remember, to find the conjugate of a complex number, you just change the sign in the middle. So here's an example. Here's a complex polynomial, z squared minus 4z plus 5, f of z it's called, and remember we use z instead of x for complex numbers. So I've found that z equals 2 plus I is a root, so by the conjugate root theorem, that means the conjugate of z, or 2 minus I, is also a root. Here's an example question. If z equals 2 plus 3i is a root of f of z equals z squared minus 4z plus 13, show that the conjugate of z equals 2 minus 3i is another root. So the conjugate root theorem tells us that the f of z will be 0 if it's a root. So let's try the f of 2 minus 3i and see what we get. So all we're going to do is we're going to replace z with 2 minus 3i in our equation. So the f of 2 minus 3i becomes, instead of z squared, 2 minus 3i to be squared, instead of 4z minus 4 times 2 minus 3i, and a plus 13. Let's tidy that up. 2 minus 3i to be squared becomes 4 minus 12i plus 9i squared. Minus 4 times 2 minus 3i becomes minus 8 plus 12i, and then a plus 13 at the end. Then tidying all that up. So 4 minus 8 plus 13 gives me 9. Minus 12i plus 12i cancel. 9i squared is 9 times minus 1. So I get 9 minus 9, which is 0. Therefore, z bar, which is 2 minus 3i, is also a root.